The next hour, I spend a little time on the introduction of the language that I use for designing all the stuff. So it is not Python, it is not MATLAB, but it is Mathematica. And I'll show you a little bit the reason why I use that. It is to play with concepts, with mathematics, with everything. And I guess most of you are not using Mathematica. Who has used Mathematica before? Only one, and one is saying a little bit. Okay. So I give an introduction from the basics, and you will see that it is quite simple. It is also used to be, that you get one-liner solutions. It's made by an American company, Wolfram, and that's the name of the guy who wrote it. This program, and it has 10 million lines of code, was written by one guy when he was 29 years old. He's a professor in theoretical physics, Stephen Wolfram. The guy is incredibly famous. He's now in the board in the United States of all kinds of advisories for high-level science and so on. He started the company Wolfram Research, and they sell this product, Mathematica. And Mathematica is now 25 years old, and it has all the same functionality as all the other programs together. So it is everything that MATLAB can do, Mathematica can do. But it is used a little bit more in the sophisticated area by the higher level mathematicians and so on. But today it has grown to a very versatile set. It is faster than MATLAB. It is much more modern in terms of appearance. It has everything, all these networks, all these packages that MATLAB has. So you have packages for wavelets, for finances, for chemistry, for whatever. Also a lot of deep learning. If you look on the website, you find all these products and so on. And I show you just the product. It is the biggest Windows application ever written. It is 4 gigabytes as an executable. So it is, and everything that's in mathematics is in there. So let's see, Introduction Mathematica. It's called .nb, that's a notebook. So we look at notebooks. It's opening now, and you see the appearance of Mathematica. It is a interpreter, and Mathematica has, in these notebooks, it has cells, like you have in notebooks in Python 2, and you see a cell here. And this cell is a section cell. If you make it a title cell, you get like this. So everything has a nice appearance. And you write text in this case, or you write code. And because you have text and code together, you easily write your full reports. It is doing all kinds of things interactively. So if you have 6 to the power of 20, it calculates it. It does 6 to the power of 200, but it doesn't matter. But this is not a nice way of writing. This is so old-fashioned. This is like MATLAB is doing it. It is actually from the 90s. You want to write it like this. So in Mathematica, we have very easy ways of doing this. So normally, if I open a new cell, for example, here, you click in it, and you say 12, and then you say Control head, and then you get this one. And then you put some big number, and you get some big number. And you have very easy keystrokes for doing this. But it also does every algebra you like. Integrals, differential geometry, eigenvalues. So if I take the eigenvalues of this small matrix, you get it. And it's numerically precise. So it does not give you a number. It gives you really the square root of this, because this is exact. If you want a number, you just specify that you say, I have a function, and I put the function in front of it, and you get the number. You could also say, instead of this, if you realize that I don't want this, that you don't put it in front of it, but you say, I put it at the end. And then you get it. You type shift return instead of return because you can enter multiple lines. You can solve equations. And now you see this is double is, because this is not an assignment that x is 2. No, this is equal to, that means double is. So you say square root of x plus a is this. And Mathematica has never abbreviations. So eigenvalues is not EV, it is eigenvalues. And all internal functions, there are more than, there are thousands of functions inside. From the factory, they are with a capital, and your functions are not with a capital. So you easily see what is what. So you have solve eigenvalues, and there are lots of them. You say, okay, I compute an integral. And here you see the integral. A very nice function is interactivity. And suppose I have the function expand, and this is expand, okay, you get this very nice quadratic mechanism. And now I want to play with this guy. I want to say, I want to manipulate this, and I want to make this 4. Okay, it's get bigger. But it should be nice to say, okay, make it n. And now I say comma, I make a function manipulate, and this n runs now from 1 to, let's say, 100. Not every value, but I want only integers, so I say in steps of 1. This function manipulate automatically generates a Java applet. So this is now a Java applet, and with this Java applet I get a slider, and I can now interactively use my n. If I want to see what n is, I click on this small plus, and you see n is 37. And you can even make movies. You can export the movies as a MPEG or AVI file or whatever. You can store your notebooks as LaTeX, as PDF, as XML, everything. Everything you want is in there. And that's quite nice. You just have to find it. And because this expand is only one function, but in this manipulate, you can do everything. Integrals, Fourier transforms, convolutions. So if you want to play with a parameter, you just say manipulate, and then you play with the parameter, and interactively, in one-liner, Mathematica plays with it. My students use this a lot. And if a paper comes in, the same afternoon, they have the paper running, the theory from that paper. It is just copy-paste the formulas. It is really nice. You can do exactly. And that's the reason I love Mathematica in the sense that it is so fast. I don't care about the language, but this is an extremely fast design. I can do always with just a few lines. It's incredibly precise. So this is the numerical value of pi. So if I do the numerical value of pi, and how do you write the pi? You say escape p escape, and then you get the pi. So the escape key is this guy, the upper left key on your keyboard. If you put it in front and behind, you can type any key. So if you take escape and then you type A escape, you get the alpha. And if you type escape capital P, you get the capital pi. So the numerical value of pi is, of course, 3 point this. But suppose I want a million digits. You type it, and you see that within a few milliseconds, you have of a fraction of a second, you have a million digit. Is it really a million digits? Well, count it. But it's quite amazing. So you can do all kinds of, and if you want to get rid of this cell, just click on this cell and delete it. So this huge cell here, you click on it and you delete it. This guy was a million, I don't want to sort it, so you delete it. This is a famous number, it's a Pizot number. And let's first have a look at the Pizot number. It's crazy. It is this crazy number to the power of 30,000. How big is it? Okay, it's quite a big number, 10 to the summand. It turns out that if I take many more digits, 6,000 or so, now this number is calculated, something very curious happens. It has a lot of zeros inside. And some guy discovered this. I can still not imagine how you could come up with that this has all these numbers inside, but some numerical things did it. And Mathematica is a super program to show these, how can you say, peculiarities. Of course, it has all the plots and whatever functions, so you can plot sinusoids, you can plot sinusoids with in 3D, of course, like all the other programs, MATLAB and so on, everything is interactive. You have here what's called the iterator, so x from 0 to 2 pi, and y. And here at the end, after the last comma, you have lots of options to make the graph as you like it. You can change everything, axes and colors and the whole thing. So you have, I don't know, some contour plots. This is a very complicated surface. And if you want the surface to be a little bit fancy, you say, OK, I have now some options like surface color and so on. And then you see I can make beautiful 3D graphics as all kind of rendering systems they do. It's all on board with just a few lines, and you just program what kind of contours you want, etc. So quite nice. To work with it, and this afternoon you go play with it, it works with functions, and everything are functions. And functions are with square brackets and not round brackets. So I typed this, this, for example, this will not work because round brackets are only for grouping. You always need square brackets. So this should be, and it should be not a small n, but it should be capital N, square bracket, pi, square bracket. Round brackets for grouping, and curled brackets are for lists. And we have lots of operations on lists. Two-dimensional lists are images. I already told the escape. Every factory function is with a capital, and you can have post functions. And you have some very handy functions that's typical for functional programming and not object-oriented programming. If I want to do f on every element of the list, and that could be a series of images that they say, OK, f is my threshold operator or edge detection operator, whatever. You do it on a whole series of images. You use the function map. So this means f of A, f of B, f of C. In underwater, it's, of course, a for loop. But for loops do not exist anymore. Of course, you can program for loops, they have it. But that's not human. We don't think in for loops. We don't care about all the bookkeeping. I don't need to know how long this is. I just want on all of them. So I don't need 4, 1, 2, 5, etc. That's ridiculous. That's old-fashioned. I want to have it immediate. You can also do pattern matching. You say, OK, I have a lot of things here. Suppose a DNA string, and there is something in this huge DNA string happening. Then you could say, OK, I just say underscore means anything. That is anything, an object. And you have here another anything. And this anything is called P, and that anything is called Q. So this little thing means a sum of two things. So if there is something in my pattern, somewhere there is a sum, it finds it. And it takes the first element of the sum, calls it P, and it takes the second one, and then I can do something, and in this case I just say, OK, take P to the power of Q. So now it finds, of course it does a for loop, it takes every element, it says not a sum, not a sum, not a sum, not a sum. OK, this is a sum. So P is now K, and Q is W, so I get K to the power W. And this pattern recognition is very powerful. You can do some image capture, and then your webcam is getting organized. So this is me. But you can do, of course, all kinds of interactive things. Suppose I want to do edge detection on the, and now you see I get real-time edge detection. You can change lots of parameters, and I just want to make it a little bit speed up. If you say the difference between two images, this one, you see, when I'm standing still, nothing happens. But now you get the difference between the frames. And this is what happens in every observation camera. If you have a gate, nothing happens. But if someone moves, you immediately find it. So this is an effective way to do video. But you can all do it now in, and that's my message here, in a one-liner. There are lots of functions. So if you have a function, for example, here, a random real between 0 and 1, and you make a matrix 1000 by 1000. So if I take random real and I say from 0 to 1, and I just take a 2 by 2, you get 4 random numbers. And now I get here a matrix of 1 million random numbers. And with dimensions, I check how big it is. And just to show, you see it's 1,000 by 1,000. It's not a sparse matrix, but a dense matrix. And now you can see, if you do an inverse of this matrix, that's quite an operation. How long does it take? It's quite amazing. It should take some time. But it's so fast that it cannot even measure here. But Mathematica is incredibly fast. And that's, I have some data analysis, but I think you believe that. We have some Fourier analysis, so let's plot some data. You take the Fourier of it, and you see nothing is abbreviated. You get the Fourier, you take the absolute, and then the list plot. And here you have it. You can solve differential equations. Anyway, this afternoon you will get a full tutorial on how to play with it, with step by step. You can go through it. Everything are notebooks. And as you see, these notebooks, they have the appearance that they are grouped. This is a group bracket. It goes from this whole section. If I double-click this group bracket, it closes. So it's very nice, and I can close this one. So it's very nice to get organized. You open and close the sections that you want to have. So, and with manipulate, you can do all kinds of interactive functions. So you see manipulate here again, and I have different parameters. I have P and R and A and L, and I all give them iterators. So L runs from 1 to 1,000 in steps of 1, and this is the initial value. L start at 300. And you draw some polygon, and now you can just play if you change the zoom factor or if you change the R. But what I want to show you is the speed of it with everything that you want to play with is now interactive and immediately available. L is not doing much, but immediately available for experimentation. And that's the main reason I want to get you to know this program. We have revolutions in everything, revolutions in cameras, in cars, in software, whatever, and this is a revolution in this high-level software. I told you already manipulate. I showed it for the expand function. You can make many sliders, as we also saw before. So if you have just a simple plot function, then you can change the amplitude, you can change the frequency, you can change the phase. It's all one line. There are thousands of demonstrations, and they are all notebooks, and you can download them. And that's quite nice. So this is actually a blog. There are 2 million Mathematica users, and they get lots of demonstrations. And here you have demonstrations in creative arts for kids, systems, models, engineering, and just have a look. And they are beautiful. They give the full code, and you have wonderful generate fractals, make robotics, you name it. It's a wonderful resource to have a look in. I want to go a little bit more in detail and let you show what is not object-oriented programming, but what is functional programming. Functional programming is very close to English, to our language. That means I don't want to reason with loops and whatever. I just want to say in normal language how it looks like. So I'm going to show you an example of functional programming. So I'm going to find in a dictionary of over 100,000 words, I'm going to find all the words that read the same when you reverse them. It's called a palindrome. And it's just a simple example. But what I do here is I say, okay, I set the directory on the notebook directory. So you see a semicolon here that is to prevent output. If you get 1 million numbers, you don't want it on the screen, so don't forget this So if you see it, this is the notebook directory, actually, that the system now knows. Then I say import, and you can import from the internet just by specifying the URL. And I import the dictionary, and I call it data. If you ask what is the length of data, 118,000. So it's a big English dictionary. And now you have some very simple things. If you want to know what is the command, what's the function, always take the English word. If you want to take the first 140 word, take data, 40. So it takes the first 40 words. If you take a range, you specify a small list. And this list is from to. So now you get somewhere in the middle, you get some words in the middle with an N. And the last is with a negative number, so you just say, take the last 5, there are this. I want to do some operations on words. And words internally are strings. And what's a string? Between quotes. So there are many string commands. So I take here the question mark, and this is the wildcard. How many string commands are there? Well, quite a few. String part, string partition, string position, string reverse, you name it. So if I take the string length from this string, I see that this string is 23 long. If I take the string reverse, it takes the string reverse. Very simple. But I don't need a loop to write or so that you say, okay, in some way I need to reverse it, begin at the end to put it in the beginning and so on. Now we're going to make some functions. And a very condensed way to make a function is to use this guy and to use a slot. So if I say square something, because that's a function, what's actually a function? A function is a machine, you put something in and something gets out. So if the function is a square, you put in a 3 and you get a 9 out. So that slot where you put something in is this hash sign. So we have a hash sign here, you put something in here, and this something is now squared, and this means it's a function. So f is a function. Let's define f. You see f is blue, that means the kernel doesn't know it yet. Mathematica consists of 2 programs, a front end, which you see now, and a calculating kernel, and they communicate all the time. So the front end sends the thing to the kernel, and the kernel sends the result back. If the kernel knows it, it gets black. So f is now black, and f means square something, and that's a function. So if I put now the function, that's square brackets, I let f function on x, what do I get? Of course, I get x squared. And if you say, my function is now more complicated, take the sign of something, minus something to the fifths, have a new f, and now I take the f of x. Indeed, you get the sign of x minus the fifths. Now let's look at palindromes. So first I phrase my task. Select from the data those words that are equal to those with string reversed, and of which the string length is larger than 2. Because words of 1 letter don't make sense, that they are the same. So I have a very simple English question here. So how is my Mathematica code? I use select. And select works on the data. So select is going to select something from the data. And how is it selecting? Well, it needs a function. So this function will be applied on every word 118,000 times. So this guy is the function. You see, it's a function because it has the ampersand at the end. So what's the function doing? It has a slot. So the first word goes in here. So aardvark. So it says, put the first word in here. Is it equal to string reverse of the word? So this is a test. And the outcome of the test is true or false. Then have another test. This is the logical OR. And then they say the string length of aardvark should be larger than 2. So this is a very simple test. So I define, and now you see within a fraction of a second it has done thousand words, and it finds all the words that read the same. But the message is here, this is functional programming. This has nothing to do with generating a for loop. This is just specifying in English what you do. If you master this, you have a great advantage in speeding up things. That's the whole thing I want to give you in this course. We have this function map. I already showed you. Map of A, of B, of C. And now I can say I want to have the string lengths of all these words. Well, map string lengths on all the elements of data. So now I do this, and it is already now, you see, let's check the dimensions. It did this 118,000 times. What is the maximum of word lengths? 45 letters. Count is another one that is functional. If I want to say how many word lengths are there that have the value 10? Well, count how many word lengths have the value of 10. This is all I have to specify. So you count the number of word lengths. So there are 14,000 letters with 14,000 words with 10 letters. What is the position of the word kayak? This is a string with double quote. So the position in this huge dictionary is 55,000. I don't want a for loop to check all of those and match equivalents. Internally, Mathematica is written in C++. So everything, of course, underwater is a for loop. But you don't want to see it. You want a high level. You want to speak to the language. And that's exactly what we're doing now. So we have the highest level language that exists today, right here. You can make a table. So you say, count all the word lengths. And now you say, let I runs to this maximum. So you get now all the word lengths here, and you plot it. And here you see the average word length of a dictionary. But all are one-liners. That's actually, I don't care about the application here, but I care about what is functional programming. You see it as an example. There are many things you could do. I have here an optical systems. I think it's another notebook. I enable the dynamics. And this is a fantastic manipulate function. And this manipulate function, you can not only manipulate with these sliders you can manipulate the color. But you see different lenses here. And look here at the end. With the different color, you get a little bit different refraction breaking. So if you go from blue to red, Mathematica calculates the properties of the glass, and they can see that with different wavelengths, you have two different. But these are points that you can move. These are called locators. And if you locate this point interactively, it calculates all the light rays. You can change the position of a lens. You can change the angle of the lens. You can change the rotation of this lens. So everything is now interactive. And this interactivity, that is the beauty of it. And this is actually in a few lines coding, you can now play. You don't have to spend a whole week on how to generate my program and do the debugging and whatever. You can directly go to the application. You want to see, hey, what happens if I make this lens thicker? Or what happens if I... So if you make this lens thicker, well, it's not so sensitive, but a little bit, and play with it. You can make this lens negative, or you make it positive, and that's the way, that is how current interactive programming works. Let's see. There is a huge documentation center. It's in the help. So if you check Wolfram documentation, then you get an enormous amount of documentation. There's a full image processing class here. So you have image segmentation, restoration, morphological analysis, computer vision. It's huge. And tomorrow I will give you in detail deep learning applications. So how to build a deep learning network step by step in this language that you can easily program one-liners and play with it. So I don't expect you to learn Mathematica completely, but I want to yeah, that you see my examples and understand what I do. And if you see the programming of the mathematics in Mathematica and you see how it works, you more easily grasp what this mathematics is actually doing. It has beautiful graphics. You can even show in graphics the opacity. So if you have, let's say, some cylinders and you see they are now transparent, that's quite nice. And you can regulate the transparency. And there are lots of visualizations. You can even show chemical data. And Mathematica keeps thousands of databases. And it has, for example, a database of, I don't know, millions of chemical substances. And you can play with it. If you want to have the molecule plot, you just show me the molecule plot, and you can just interactively in 3D see. And there are so many substances, so this is what ends on ation. You get those. And then you can just have a look at how do they look like, and you just map the molecule plots on all of them and have a look and how do they differ and are these metamers and whatever. So it is a nice tool that most people don't know, but just have a look and discover it. You can all put them in a grid, so you can nicely put them in your report and you generate like this. If you save Mathematica, you can say save as, and there are many ways to save it. You can save it as XML, I already said, as LaTeX, and you compile it and it all works. So it's very convenient. The last section I want to show is some neuromathematics. And this is an example of what I will do the rest of the coming weeks, and I give you an appetizer of it. And I want to make you critical. If we look at images and so on, many people take for granted all kinds of things that we have done for decades. And if you see, for example, an image like this, what's this image? Most of you will recognize that's me. And how do you see that? Because you blur a little bit this image. Because what is wrong with this image? This is zoomed out. It was a very tiny image, and you zoom it out. And we normally take this for granted. And we say, OK, we have square pixels. But actually, we have a lot of junk in the image now. We have edges, we have corners, and I really don't have corners in my face. So something is wrong. This is the wrong pixel. We never should use square pixels. They're very easy for industry to make, because you just cut rows and columns and you have pixels. But it's a disaster for computer vision. So we should have circular pixels, of course. And we should have pixels with a smooth boundary. I don't want edges. I don't want corners. So we need to think a little bit. Nature doesn't take square pixels. There's not a single retina with square pixels. And this is the reason. So we're quite stupid. And there are many things you will see during this course that we take for granted. That people say, yeah, we do this already for decades, but it's actually wrong. So if you get critical, and let's see how we can do this. I first set some parameters, because I want my function plot 3D always with that it plots all the numbers, and it spits out an image size of 250. And the function array plot, I want it in gray, no frame. And I have the function GD, that's called the Gaussian derivative. I'll need it later. OK, I import this image from the internet. Let's do it again. And now you see the image. And the title of this part was, what is the best shape of a pixel? And how can I do the reasoning for this? Well, then we need first principles. We need to set a couple of constraints, a couple of, what are the requirements? So what are first principles? Well, first of all, we do a measurement. We measure light in every pixel. And that aperture is finite. That has a size. And the reason it has a size is that I cannot see everything. You have molecules and everything, but I cannot see them because my pixels are too big. So I always do blurring because my aperture is finite. So I have some area in which I measure the light. And everybody wants to make it smaller and smaller. My smartphone has already 12 megapixels, so that is in one micron. But it's not 0, because otherwise, if we make it 0, then it's fine. And we will see later that if you take a derivative, you take the difference of 2, and you remember the high school formula, fx minus fx plus h, and then you divide by h. You make h to 0, and that's the derivative. You cannot do this with pixels, because I cannot go to 0. Everybody wants to go, scale is 0, but we cannot. So we have a finite aperture. We have to live with that. This aperture is scanning all over the place. And we want every place to be treated in the same way. That's the logical way. I don't want to have another measurement here than there. So it is invariant for translation. That's the way we call that. We're going to discuss next week invariance in much more detail. We want the measurement to be linear. Double in, double out. Because in nonlinearity, we need knowledge. What is then a nonlinearity? To the square, to the third? I don't have this knowledge. I know nothing. So I have a linear operator. All of this implies automatically that this must be a convolution, scanning all over the place. So this is my L, my luminance, that's U, the light that's coming in, the whole light pattern, and G is my pixel. And I want to know what is the best formula for this aperture function. Is it a circle? Is it a cylinder box? Is it whatever? So we need to calculate G. And this is a convolution. I scan G all over L, and the output is called H. I do it in 1D, so alpha is how much I shift, and I shift from all the way left to all the way right. So I start with this integral. Now I have 3 constraints. First of all, this filter should not change my intensity. I don't want to multiply this filter by 2 or a half, so the integral of this function is 1. It's called a normalized filter. The filter should not multiply the data with something other than 1. The mean of the filter, so what's coming out, that's the first moment, x times g, that can be any value. I don't know what I measure, so that could be anything. Because it could be anything, I take for simplicity, let's take x is 0. That makes all the calculations a little bit easier. But in principle, it doesn't matter. And what's the size? That's actually the variance. And the variance, that is the width of a standard deviation, the sigma. We also call that sigma. It's the second moment. So x squared times x. And how do we call that sigma? Because we have x squared here, we also call that sigma squared here. So we have the size is sigma squared. You can call it the scale or the aperture size or whatever. And now comes the biggest one. We want to have as little spurious artifacts, no edges, no corners as possible. So no junk, no disorder. And what is disorder in physics? That's entropy. Entropy, chaos. And the formula for entropy is this, G ln G, and we call that H. So now we look for the G, for which the entropy is minimal, given the constraints. And now we have to look into mathematics. How do we calculate a minimal of a function with constraints? Well, there's a whole field of mathematics that does that, and that is optimization theory, and we use here the method of Euler-Lagrange. Some of you will see this for the first time. It's an Euler-Lagrange method, but I'll explain it to you. It's actually quite simple. It has a beautiful name. Well, how does it work? Euler said, well, you have to combine all of them. So you just say, take the entropy here, take the first constraint, that it should be a normalized filter, take the second constraint, that the mean is something, and take the third constraint, we have the variance. But I don't know how much I should add, so I put some constants here, lambda 1, and lambda 2, and lambda 3. And I call this my energy. And all of this should get minimal, so I want to have the minimal entropy, but also minimum with these constraints added. And the problem is, of course, yeah, I don't know G, I don't know lambda 1, lambda 2, lambda 3, so what to do? Well, first of all, you say we want to have a minimum. And this is not the minimum. So I take the derivative to g. This is not the derivative to x. This is the derivative to a function. It's a little bit different. The derivative to a function, and if you take the derivative, so actually this means I'm going to play with g. I take a variation of g, and I'm going to look what this e is doing. And if I'm in the bottom, I'm 0. So I want this derivative to this function g to be 0. And these lambdas are called the Lagrange multipliers. In Mathematica, we go do this, and we call this dE dg, we call that var, variation. And if you take a derivative to a function, you use a function that's called variational d. D stands for derivative. Okay, so let's take the variational d, and I take my function here, and now you see I got something interesting. This guy, it should be 0, of course. What happens if I take the derivative of this function here? Well, with the derivative, that is the opposite of integral, I remove the integral. Okay, the integral is removed. And because this whole thing is 0, and every term has gx in it, you see gx here, gx there, gx here, we divide by gx, so we get this. So this guy only leaves me the x. We have the x here, times lambda 1. So this expression is quite simple. It has a logarithm. Okay, let's solve this expression. So I now say variation is 0. Let's solve it for g. And we plug in this g, and we solve it. And now we see g is an exponential function. Let's make it a little bit bigger. On the left lower end, you see you have a scale, you can make it bigger. So I already see that my aperture function is an exponential function. But I still have this lambda 1, lambda 2, and lambda 3. How do I find them? Well, if I have 3 unknowns, I need to make 3 equations. That's the first statement in algebra. If you have 2 equations and 2 unknowns, you can solve it. You have 1,000 equations and 1,000 unknowns, you can solve it. So I need to make 3 equations. Well, I know that the integral of this guy should be 1. So if I take this g and I plug it in here, and I let Mathematica, so if I ask what is gx, Mathematica knows it is this guy. So if I now ask to Mathematica, let's delete all output, so I have to. Where am I? Yeah. So I'll let Mathematica now calculate this function. You see that the integral of this exponential g is equal to 1. And I know that lambda 3 should be 0. I help Mathematica a little bit because let's get g again. You see lambda 3 is here. And if lambda 3 gets really big, well, this explodes. And that's not normal. So we already know that lambda 3 should be negative. So we add it. OK, we let Mathematica do the calculations. It's not easy to do an integral of this exponential function, but that's why we use Mathematica, and whoop, here it is. It's an equation, it has this double S, so the first equation we have. And the second equation is that x times this function, the mean, that should be 0. Okay, let's see what comes out. Crunch, crunch. Oh, very simple, lambda 2 is 0. But here you see I still have lambda 2, lambda 3, lambda 1. Now we take the third one, and in the top you will see when it is, you see on the very top line, you see here running. And the third equation is this one. So now we have 3 equations with 3 unknowns, lambda 1, lambda 2, and lambda 3. And now we say, make the solution and just say solve these 3 equations, that's a list between brackets, for these 3 unknowns. And we spit out reals. Okay. we get a solution. We see that lambda 1 is 1 plus the logarithm of this, lambda 2 is 0, and lambda 3 is this. And it's indeed negative, because this is always positive, there's a square. So we come in the direction, but now we have to plug in these lambdas in e to the power this. And then we use in Mathematica this means replace. So we take the solution. The solution is this whole set. We have too many brackets here, so that is 2, so we say flatten. That removes the brackets except the last ones. And we just replace all these lambdas. And there we go. Oops. We get a single solution. And that's nice. So this is the optimal shape of a pixel. And what is this? Well, this is the Gaussian function. This is the dumbbell curve. This is the normal distribution. This is the Gaussian. So the Gaussian is the best pixel, given from very simple, actually, constraints, first principles. If I know nothing, if I scan everywhere the same, and I just don't want any not existing junk, use the Gaussian. And there are not many Gaussians. No, there is just a single solution. So this is beautiful. So let's plot this Gaussian. Very simple. All know this Gaussian. This way of reasoning has been triggered by a lot of mathematicians who say, hey, we like this. And there are 11 different ways of deriving this Gaussian. It turns out, I have just a few minutes left, that the derivatives of the Gaussian are also a solution. So let's take the Gaussian. And we see the Gaussian here. It is a function of x squared. Here we see the Gaussian. X squared divided by 2 sigma squared. And this is a normalization function. This means the area is just 1. If I integrate this function in Mathematica, I get 2 pi sigma, and then I divide by it. If you multiply this guy by the same with y, this x squared and y squared, they add up. And you see they add up here. And you already see the function of a circle here. So a 2D Gaussian is a circle. So let's make a 2D Gaussian here. And I plot this 2D Gaussian. And you beautifully see, yes, it's a circle. So this is the optimal pixel. And this is the sensitivity value of an optimal pixel. And we're going to look at this a lot. And this is the way you take derivatives. You say, OK, partial derivative to x. Just write partial derivative to x of g. And now you get the x derivative. Well, this is the x derivative of my Gaussian kernel. I can also take it in the y direction. And you get in the vertical direction, you get a derivative. These, we will see that tomorrow, are the first filters in our deep learning layer. We will see that these are actually Gaussian derivatives. And not to the first order, but we also take them to the second order. So here we have to x and y. So this is a more complex filter. We can even take 6-order derivatives, 4 times 2x, 2 times 2y. So we get all kinds of complex derivatives, and they look like this. Very strange. And actually, these filters take the derivative of your image. Because what happens if I have an image, and this is my image Lx, and I convolve it with my optimal pixel, with my Gaussian, then this is the convolution. But now I want to take the derivative of this convolution to calculate edges, because the first derivative is nothing else than edge detection. The second derivative is corner detection, and is curvature. So if I take the derivative of this guy, I can also put this derivative inside. So these are all linear operations. So I put this derivative in front of the g, so I get this. So this means I can do a convolution with the derivative of a Gaussian. And then you do 2 things at once. You have an aperture and you measure, and you take a derivative. Well, that's exactly what V1 is doing in our visual system. So it takes high-order derivatives of our visual surrounding. And tomorrow we're going to see what has been measured and to what order and at what orientation and what scale, etc. So we have a very stable operation now. Differentiation is very unstable, but differentiation is now done by integration, because it is the convolution integral. And now we can do differential geometry to high order. And these are called regularized multi-scale differential operators. It's a little bit an introduction to what's coming. But we have the Gaussian as a regularizer. We can go to any order we like. We can take 20th order derivatives. And we're going to have a look. What do they mean? I only know first order. I have no idea about second order and third order. But we're going to look at these orders in great detail. What is a second order actually doing? Why should the visual system measure second order? So we're going to look at the second order. The first order is a vector, ddx, ddy. It's called the nabla operator. A second order is d2l dx2. So that's a second order derivative. But I have many of them. I also have lxx, second order. I have also lxy. I have lyx and lyy. That's a matrix. So we're going to study in second order what's the matrix. And it turns out that the eigenvalues of this matrix are beautiful. They're principal curvatures. And our visual system seems to measure this all over the place because we have lots and lots of these second order derivative detectors. And they are very critical for shape. Well, we know that for a long time. Well, that will be the lecture differential structure. That's beginning next week. This was an introduction to Mathematica. I stop here, given the time. The rest you can see this afternoon. You see that it's a powerful language. Play this afternoon. We have a matrix. We have a special session. We go install it for all of us. We go download it. For those who don't have it, I have it on a USB stick. It's quite big. You're going to do some first experiments. You go through a tutorial and have several things that you can read through, but it is to get you a little bit acquainted with this powerful mechanism. You have Python, you have MATLAB, you have all the other things. I just want to give you this as an extra tool to play with high-level things in an easy way. If you want to do this differential stuff in Python, it takes forever, and you got stuck, and you got all kind of whatever. You have now a nice tool. So that will be the afternoon. And tomorrow we go into physiology. So then I spend a couple of hours on what's happening in the brain. Have a good lunch. And, oh yeah, we go take a picture, because we are all together now. If we have the stairway to the canteen, let's all stand on the stairway. Then we have you all lined up. And I ask a victim to take a picture of all of us. Thank you very much.